Okay, let's continue the lecture. So talking about the masking material for HNA system. Actually, HNA system is a very strong oxidation and also etching system. So not many material can resist this kind of etching. So the masking material sometimes is very difficult to find, actually. Okay, so here give you some ideas about what kind of things we can use. Actually, if you use a silicon dioxide based material, actually they cannot resist for a long time. So maybe for a short time it's okay, but for a long time it's really not good. And photoresist is very, very bad, actually. So in this strong oxidation X the environment, photoresist can be peeled off quite easily in very short time, less than 1 minute. Okay, so that's why we need a hard back for the photoresist. Very, very hard back. That means a very high temperature, more than 150, even 180 degrees C for photoresist. So silicon dioxide photoresist not good. So the best one I think is LPCB silicon nitride as a mask. Even the silicon nitride can be etched by the HF, hydrofluoric acid, but still can sustain for a little bit longer time. And so I think so far silicon nitride is the best material to resist this kind of HNA etching system. Sometimes people use gold, okay, but gold does not have good adhesion to silicon substrate. So usually we will put the chrominum, okay, underneath. But consider chrominum can be etched away by HF. So we need to put a very thin layer chrominum and a very thick layer of gold to maintain the mechanical integrity of the etching system. Okay, so this is a rough idea for your reference if you in the future you are going to use this as your method for making structure. So now we will go to the next topic, the most important one for today's lecture. So now we are talking about the anisotropic silicon wet etching. For anisotropic silicon wet etching, actually, first we need to consider the silicon structures. Okay, so we can classify silicon structure at least as 3 different types. The first one we call amorphous type. Amorphous type, that means the molecules or atoms inside silicon substrates, there is no orientation, no orders. Okay, they arranged randomly, distributed randomly inside a silicon substrate. That's we call it amorphous. The second type we call it polycrystalline or polysilicon. That means we have a lot of small single crystalline things, but they contact with each other with different orientation and also some boundary, grain boundaries over there. So we can consider polycrystalline is a composition of a lot of single crystalline crystals, okay, or grains contact with each other. So we call it polycrystalline type. So this one is the best one. Is a single crystalline, okay? That means the atoms are arranged in very, very good orders, follow the structures very well, okay? So without any boundaries, okay? This is called a single crystalline. So all the silicon wafer we are using is a single crystalline silicon, okay? They through the growth of a silicon crystal process, then cut into pieces, then we use them, okay, in different directions, okay? So when we look into the single crystalline silicon, actually the metallic structure, the atomic structure looks like this. It's an interlocked fast-centered cubic. So that means a two-century facet cubic. They interlock together, become this structure. Okay. So when you look into the detail of the atoms, the bond connect to each other, you can find out that the structure is more like a diamond structure. Actually, it's diamond structure because silicon can form 4 covalent bond with other different atoms. So it can form like a diamond-like structures. So when you consider one of the atoms, for example, the black one here. So the black one you can see connected with the top with the other 2 atoms on the top, and the other two on the bottom. And these two bonds rotate at 90 degree to each other, okay? So they can form most, flexible, most comfortable position actually, okay, in the space, okay. So each of them, you can form similar bonds with each other. So in order, you can become like a centric, fast-centric cubic structures, two interlocked together, okay. So in this kind of single crystal silicon, actually we'll consider three important phases. Actually, there are many different phases. We especially consider three important phases, because in the next step, we will introduce different etching rate, okay, on these three specific phases. So that's why we will mention the direction and also orientation, okay. So the first one we call the 100 plane. For the 100 plane, when you look into the atomic structure into the 100 plane, you can see they form like a rectangle structures, very uniformly distributed. So, for example, the 100 plane look into, so like a rectangle structures, very uniformly aligned to each other. Okay, that's when you look into the 100 planes. Okay. So this one, you need to rotate this structure by 45 degrees, okay? So you can end up, looks like this. So you can see the structure become rows and the columns in 45 degree orientation, okay? So this is what we call the 100 plane, okay? So when we use in the 100, that means that it's called a Miller index. The way to, actually, the Miller index indicated the orientation of the plane, the vertical direction of the plane, okay? So if you put the coordinate system x, y, z axis over here, so 100 means it toward the x equals 0 direction, okay? The first x equal s equals 1, sorry, s equals 1, other equals 0 direction, okay. So so that means this is a 100 plane. So when you talk about the other 110 plane, 110 plane means it faces out the other direction is 45 degree to the 100 plane, okay. It's like this. So for the 110 plane, so look into the surface we're intact with 6 atoms. 1, 2, 3, 4, 5, 6. Sorry, not 6. 1, 2, 3, 4, 5, 6. 8 atoms. 1, 2, 3, 4, 5, 6, 7, 8 atoms in the space. And the structure is more like it's a hexagon structure. It's not a uniform hexagon. Has one side a little bit larger than the other sides. Okay. Okay, this is 110 plane. So we talked about the 111 plane. One plane means the direction is 111 direction. So you can see the three intersection is 111 on the space, and so you can have this plane interact with 1, 2, 3, 4, 5, 6, 8. Okay, 1, 2, 3, 4, 5, 6. Only 6 atoms. So the 6 atoms form triangle. You can see triangular structure. But when you put them into the space, okay, they form triangular structure here, and pair by pair. Okay, so when you look into this triangle and the other two triangles on the bottom, so they form a hexagon structure. So for example, you look into these 3 atoms on the top. Actually, there are 3 atoms on the bottom as well. So these 6 atoms form a hexagon structure. So this direction gives you the highest density of a silicon single crystalline structure. Highest density. So density for this direction is twice as high as this one in the other direction. Okay, it's much denser. Okay, so why do we concern about the orientation and also the density? Because afterward, we will discuss about the etching rate on different phase. Actually, the 111 phase is the phase you got the slowest etching rate. The etching almost stopped over here for some special chemicals. Okay, so this phase is important phase. And also on the other hand, on 100 or 110 surface, the etching rate is much faster than the 111 surface. Okay, so that's why in the current stage we need to understand the crystal orientation, in order to understand why the etching always stop at a certain kind of spatial space and the form spatial structure. Okay. So now give you a rough idea. Okay. So the mirror index here. Okay, we have several denotation. So first of all, for example, we have a one plane. Okay, in a space. So we first take the intersections of the faces to three axes. For example, 111 plane, you take a 111 intersection of the plane to the coordinate axis. Okay, then take a reciprocal 1/1. Okay, and then finally to take the integer of this set. Okay, you become the mirror index. So the meaning of the mirror index actually is the vertical direction of the face actually. Okay, understand? Okay, mirror index. But you take an integer numbers to represent the direction. Okay. So we have different notation. Please remember, if we put the 100 inside this kind of assembly, that means it's the 100 series plane. 100 plane actually in a space we have a 610 plane, right? Related plane because if, for example, like 100, 010, 001, minus 10, 0 and 0 minus 10 and 00 minus 1. Okay, let me write down. Okay, this symbol, this is the notation. Okay, assembly of 100, 010, 001, minus 100, 0 minus 10, 00 minus 1. The collection of these 6 planes. Okay. Why do we do this? Because these planes share the same property. When you look into either one of them, so the atomic structures are the same, right? So it's like a rectangle structures. No matter you look from 100 or minus 100 or 0 minus 10, they look similar. Okay, sorry, not this one. Okay, so the metallic structure is like a rectangle structure, this one. So this is just a diamond structure. Okay, I just put diamond structure rotate into certain kind of space, so you can see the structure change. So when you look into, yeah, this is one, almost there. Okay, yeah, here. Do you see? So when we project these atomic structures onto the screen, you can see the rectangle structure among them. So that means that this direction is 100 series direction. Understand? Okay. From the same crystal, if you rotate different direction, you can see different phase. So this is 100 phase. Okay. So when you rotate into the other one, this is 110. You can see 6 atoms like hexagon structure, but it's not symmetric. It's not symmetrical. But on the other hand, if you rotate into the other direction, almost there. Oh, no, it's not. Okay, not easy. Here, okay. See the hexagon structure, the right hexagon structure. So this right hexagon structure is exactly the same as the things showing on our left-hand side. See, 6 atoms, 3 on top and 3 on bottom. So totally 6 atoms. They integrate together, become you can look into this one, right? It's a hexagon structure. So this is a 111 plane, highest density structure. So the same crystal, I give different orientation. You can see different density, okay, of the atoms arranged into the space, okay. So that's why they give you different, action rate. Okay, one from the density, the other one from the bond strength. Okay, for example, if you want to take one atom, for example, from this kind of structure, take this one atom out from this structure. So you need to deal with three bonds underneath, right? So this is not easy when you compare to the other one. You want to take out one atom from the array, you need to deal with only 2 bonds underneath. It'll be easier. Okay, so that's why the action rate on 111 plane usually is the slowest one. Okay. Okay, so now according to the mirror index, so 100 series plane is an assembly of 6 different planes together, right? So consider the other 2 planes. 110 planes, the assembly 100 planes will be how many faces assembled together? How many? Give me the numbers first. This is a combination similar to this idea. Can you do a calculation? And also the last question for 111 surface is how many faces combined together, assembled together? $12? Great. Yeah, it's 12. How about 111? There are 12 faces related to 110. Okay? How about 111? How many of them? You can do all the combination. Find a different one. Okay. How many? 8. Correct. Yeah. Wonderful. You are great. Okay. Yeah. So we have 6, 100, 12, 110, and 8, 111. Okay. So you can come back home to write down all of these related plans. Okay, by yourself, following the same rules here. Okay. Do the combination. Okay, so it's hard to remember, right? So now you got like 28 plans over there. It's very difficult to remember. So that's why we need to make a toys like this. Okay, the toys is called a silicon single crystalline cubic. Okay, so the cubic give you all 28 plans here. Okay, so for example, on the top, bottom, left, right, front, rear. Next 6 planes, 6 planes are 100 planes. Okay, that means x-axis, positive x-axis, negative x-axis, positive y, positive z, negative z. Next 6 are 100 plane. Okay. So for 110 plane is a little bit difficult. So you need to combine 2 100 plane, rotate 45 degrees. You got a 110 plane. For example, you have a positive x, positive y. Positive. You call this x. This x. For this x is z. X and z between them is a 45-degree plane. So this one is 110, right? So you combine positive z, positive y. You got the other 110 plane here. Okay. So you got there's a positive y and a negative x, positive y, negative x. You got the other 110. So on the top you have 1, 2, 3, 4 on the top, 110 plane. On the in the center you have 1, 2, 3, 4, the other 4. On the bottom you have the other 4. So totally 12 surfaces. 110 surfaces. Understand? Okay. Okay. The last one is a 111 surface. So the one-on-one surface have an intersection to 3 axes with the equal distance. Okay, so so you need to consider one-on-one plane is a 100 plane to rotate another angle. Okay, it's difficult to say. Okay, the angle here. So those small parts are the 111 plane. 1, 2, 3, 4 on the top. The other 1, 2, 3, 4 on the bottom. So this 8 triangle form the right 8-phase structures. Those are 111 plane structures. Okay. So remember, our slowest surface is 111 surface. So those 111 surface, you collect them become a final structure. They will be the final shape. No matter what kind of edge you use, they will be the stopping surface you will have. Okay. So remember. So that's why I actually I got this from my school, so UCLA. So actually from UC Berkeley actually, they fabricate this kind of cubic. So there are some information inside the cubic, so you can do it by yourself later on. Okay, after you finish the class. But it's not easy for beginner to understand so many surfaces. That's why I simplify the structure into only 8 surfaces. That'll be easier for you. Okay, this is from my class. Okay, so for example, so you put all 111 surface together. Okay, you define your 3 coordinate system. So for example, this is the x-axis, y-axis, and z-axis. So the apex direction will facing 100 related direction. So if 1, 2, 6, 4, 5, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 6 axes, right? Related to 100 surface. Okay, this is the apex, 6 apex. Okay, and the line, expand the line a little bit. The line, if you connect the line, the center of the line, to the center of the cubic, you got a direction of 110 direction. You got a 100 direction here and a 110 direction here. Oh, say it again. Okay, let's start again. So we have a x-axis over here, y over here, z over here, right? So you have x is a negative y. So x and a negative y will form another 110 direction, right? You rotate 45 degrees here. So each line, if you connect the center to outside, there's you expand this line into a surface, it's become 110 surface. So how many lines you have? You have a top 1, 2, 3, 4, 4 lines on the top. Center 1, 2, 3, 4, 5 at the center. And 1, 2, 3, 4, 5 on the bottom. So totally 12 lines. The 12 lines represent the 12 surface, 110 surface. But we just push them into a small line. Actually, if we expand them, it will become a surface, okay, a plane. But now we shrink them into a line. Very easier for you to understand. Because the important part is this final, the A surface from the 111 plane. Okay, A surface from 111 plane. So when you look at these 2 cubic, okay. So now they are facing exactly the same orientation. Okay, except I extend the triangle, the 111 surface part, into very large, and then push all the other direction into either a point or a line. Okay, so they are the same, but I expand the 111 surface, become large. Okay, so you need to make it your own, this kind of toys. So we can use this toy in your first midterm. It's allowed, okay? So you can bring this toy with you and to help you to think of the question. Okay, how to solve the question from the toys. It's important, okay? Yeah, I know it's very difficult. My first time heard of these things, I spent like 1 month to figure it out. But for you, have only like 2 or 3 weeks. So a little bit shorter than my time, so it's okay, yeah. Okay. Can you figure it out? So we have a 6 100 surface, 12 110 surface, and the 8 111 surface. So we connect all the 111 surface, become the right 3-facet cubic here. 8 surface cubic here. 8 surface cubic. Okay, why this is important? Because when you look into the etching results, all the etching results stop at this kind of cubic structure. This cubic structure. So the difference is which direction you look into. So if you look from the top to the bottom, you see pyramid structure, right? That's the most familiar structure you will have from all the textbooks. But the other two directions is not that familiar. You are not very familiar with them. The other two, so if you look from the 100 direction down, you see the pyramid structure either on the top or the bottom, right? The pyramid structure. When you look from the 100 direction down, okay, you see so what kind of things? You see the 6-phase structure. The 6-phase structure have a 4 vertical plane and 2 inclined plane. It's like a bottom of a boat, right? A 6-phase structure. Okay. Now, if we look through the 111 direction, what do you see? 7-phase structure underneath, right? You have a 7-phase under here. So you have a 6-phase face up triangle face up, 3 face up, 3 face down, 1 on the bottom. Okay, this is when you look from the 111 direction into the crystal. So it becomes very easy. No matter what kind of a direction you look into this crystal, you can use this one to define your final structures. Okay? Understand? From 100 direction, it becomes pyramid. Okay? 4 phase underneath. 1, 2, 3, 4, 4 phase is pyramid structure. It's from 100 direction down. If from 110 direction down, you see 6 phase, 4 vertical phase, 2 inclined phase underneath. When you look into, dropped it. The 111 direction, you have 7 phases underneath. Okay, 3 triangle face up, 3 triangle face down, 1 at the bottom, totally 7 faces underneath.